This is chapter P.7, Rational Expressions, day 1. Rational expressions are fractions where the numerator and denominator are both polynomials. When we deal with rational expressions, we have to consider domain and eventually range. But our domain is considered to be the values that can be considered for a variable without causing an error. And there are certain restrictions called domain restrictions that we will show you that cause errors when you try to plug in specific numbers. And all the other numbers that work when plugged into the variable are within the domain. So generally speaking, if there are no restrictions on a variable expression, the domain will be all real numbers. And that symbol looks like this capital R here with a double line going vertically. Okay, so the domain will be all real numbers unless there is a restriction. The first restriction is when there is a variable expression in the denominator. The numerator, it doesn't matter. We could have a variable expression in the numerator. But if we have a variable or a variable expression in the denominator, that's when we have a problem. The reason being that there would be a problem is because you cannot have 0 be in the denominator of a fraction, otherwise your fraction would be undefined. So whatever the variable expression is, we know that that variable or that variable expression cannot equal 0. And when we consider the fact that this one is just x, and we know that it cannot be 0, we write our domain one of two ways. We can write it as an inequality where x such that x cannot equal 0, and we could write it like this, or we can write it in interval notation. Well, if our domain can be anything other than 0, what we want to do is we want to write interval notation going from -infinity all the way to 0, but we're going to put a parenthesis on the 0 because we aren't going to actually equal the 0. And then we're going to have this as a union with the interval notation going from 0 to +infinity. I apologize for these pop-up things here. I don't know why that's happening. So our interval notation goes from, let's see if I can get rid of that box there. Okay, -infinity to 0. We skip over the 0, and then we go on to +infinity. So that's kind of how you can think about this. The fact that these are parentheses here for the 0 means that we're skipping over the 0. Okay? Another example is an actual expression here. So if I have x plus 1 in the denominator, it is the x plus 1 that cannot equal to 0. So if I solve this for x, leaving the inequality not equal to, I would get x cannot equal to -1. And I would write the same thing for my inequality. I would write x such that x cannot equal -1. And my interval notation would look exactly like what I have up there, but we're skipping over the value of -1. So I go from -infinity to -1, union -1 to +infinity. And that means I'm including every value possible, but I am skipping over -1. And now what if we have a trinomial that was factored, And now we have two factors in the denominator. Well, that means we have to consider both of these. So if I have x plus 4, let me get back to a thin pen here. Sorry. If I have x plus 4, that cannot equal 0. But I also need to have x minus 3 to be not equal 0. And when I solve these, I would subtract 4 up here, and I would get x cannot equal negative 4. When I solve for the other one, I would add 3 to both sides, and I would get x cannot equal 3. It's really annoying. Sorry. So I have the fact that I cannot have x equal 4, and I cannot have x equal to 3. So I could write x such that x cannot equal 4, comma, x cannot equal 3. In my interval notation, we need to go from negative infinity to the smaller value of negative 4. And again, we're going to have the parentheses here. Now, we can't just go from negative 4 to infinity because we have to skip over the 3. So we're going to have a union, and we're going to go from negative 4 to the 3, and then we can finally go from the 3 all the way to positive infinity. So this is showing that we're going from negative infinity all the way to positive infinity, once we include all three of these interval notations, but we're skipping over negative 4 and we're skipping over the positive 3. Okay? So that is the first type of restriction, when we have a variable expression in the denominator of a fraction. Another restriction is when the variable expression is under an even radical. So like the square root of 2x. If I have the square root of 2x and I think about the square root, I cannot take the square root of negative numbers. I have to have 0 or positive numbers underneath that radical. So the variable expression that is underneath the radical, in this case it's 2x, that has to be greater than or equal to 0. I cannot be a negative number. And so to figure out the values of x that work for this expression, I have to solve this inequality. I would divide by 2, and 0 divided by 2 is still 0, so x has to be greater than or equal to 0. So my inequality is x such that x is greater than or equal to 0, and my interval notation is going from 0, and it's equal to 0, so I have to do a bracket, and then I go all the way to infinity. So these are my domains. I guess I didn't say that. But yeah, these are the domain of the expression. Same thing with up here. This is the domain right here. That's the domain. Okay, so this is the domain right here. We have is the domain. And down here, that's our domain. Okay, now here is another one, but it's a fourth root. Still an even number, so we do have a restriction. If it was cube root, it would be fine, no restriction. If it was an odd number out here, no restriction at all. Even numbers, we have a restriction. Okay, but we aren't going to change the way we think about this because it still has to be greater than or equal to 0. So the fact that we have x plus 2, that variable expression has to be greater than or equal to 0. When I solve this, I subtract the 2, and I get x has to be greater than or equal to negative 2. So the domain as an inequality is x such that x is greater than or equal to negative 2. And as interval notation, I would go from -2. We are equal to this, so we could have we need a bracket, and this goes on to infinity. Greater than, there's no limitation, it never stops, goes all the way to infinity. So there is our domain for the fourth root of x plus 2. The final restriction is basically a combination of the first two. If we have a variable expression that's in the denominator and under the even radical, okay, we have to consider, first of all, the radical says it cannot be negative. The fact that it's in the denominator cannot equal 0. So in the second restriction, we said greater than or equal to. In this case, the variable expression has to be just greater than 0. We cannot equal 0. So now when we solve this, we would subtract the 5. We would get x is greater than -5. So our domain as an inequality is x such that x is greater than -5. And as interval notation, we start at the -5. We are not equal to it, so we use a parenthesis. Because it's greater than and it never stops, we go all the way to infinity. And this is our domain. Now, if you see the variable up there, I just covered that. The variable up here does not affect anything. A variable in the numerator, there is no problem at all. Unless, of course, there's a restriction like the square root, which actually I'm going to cover right here, down here. Okay, again, we have x plus 3 in the numerator, no problem there. But the radical of a variable expression in the denominator has to be positive. No zeros, no negatives. So the 3x plus 8 has to be greater than 0. I'm going to solve this inequality. I'm going to subtract 8. I get 3x is greater than -8. I divide by 3, and I get x has to be greater than -8/3. You don't need to change that to a mixed number. Just leave it as -8/3. And so our domain as an inequality is x such that x is greater than -8/3. And as interval notation, we start at the -8/3. We are not equal to it, so we're putting a parenthesis, and we're going all the way to infinity because it's just greater than, means there's no upper limit. And that's our interval notation for the domain. And there we go. Last but not least, we have this example where we have more than one restriction involved. In our numerator, we have a radical, which means the x plus 5 has to be greater than or equal to 0. In the denominator, we have x plus 2. The denominator cannot equal 0, so the fact that we have x plus 2 down there, that cannot equal 0. Now we're going to solve these individually. We subtract 5. We get x has to be greater than -5. Over here, we subtract the 2. X cannot equal -2. Now, when we write out our domain, we have to consider both of these. Since the value that we cannot equal, the -2, is greater than -5, when we show our inequality here, we are going to have x such that x is greater than or equal to -5, comma, x cannot equal 2. And that should be fine. And as interval notation, we have to consider the fact that our lowest value that here listed is -5. We can be equal to it, so it's a bracket. We aren't just going to infinity because we have to skip over the value of -2. So we have to put comma -2, put a parenthesis there with a union symbol, and then start back at -2 and finally go to positive infinity. And so our interval notation does go from -5 to infinity while we are skipping over -2. And here's our domain. Whoops. Okay. There. And that's it for day 1.